Now our next method is Brents method. Now, until now we have seen the approach which based on linear approximations. Okay, so basically we begin, for example, in Newton-Raphson we begin from a point and we calculate the derivative and we draw a straight line and go to the try to get close to the root. What if we use a higher order approximation? For example, quadratic approximation. Now in this case we need to evaluate the function 3 times at 3 different points, right? So as you see in the figure, for example, we can choose this point, and this point. So this is 1, 2 and somewhere here 4. This is what the function is. So we evaluate the function in these points and we write x as a function of y. And then we try to find the root of the function, because we want x to be equal to 0. So in order to do that, what we do is we first write a polynomial, okay, which we call Lagrange polynomial. We will see it also in detail. Simply we evaluate the function at 3 points, okay. Let's say I minus 1 and I minus 2. Okay. Now you see how we write the Lagrange polynomials. So basically this is the polynomial which passes from xi minus 2 at points yi minus 1 and yi minus 2. As you see in the first term, we exclude the y minus yi minus 2. Now in the second term, the terms related with the I minus 1 is excluded, and in the third one the terms related with the xi is excluded. Now we say that from here we can approximate the xi plus 1. So at each point we need to evaluate, because we want y to be equal to is to be equal to 0. So just substituting 0 here, 0 here, 0 here, and 0 here, 0 here, and 0 here, then we say that gy is equal to xi plus 1, because we want to calculate the inverse of the function somehow, and we do it by using an interpolation. This is the basic idea of the Brents method. Then we reach to xi plus 1, and from here we can approximate the root. Here we have the algorithm for the Brents method. So this is the first part of the algorithm, and in the next slide we have the second part of the Brents method, the algorithm for the Brents method. Okay, now what if we have multiple roots? well, certainly this is a little bit of a problem because many of the methods that we have discussed will fail in this case. Of course, for example, we may have a double root at a point. In fact, at this point the derivative will be 0. This means that Newton-Raphson or second method will fail in such kind of a function if you want to reach this root. Or you may have triple point. In this case, the bracketing methods also will possess some other challenges. In fact, Newton-Raphson may fail also. We have discussed it. We may have quadruple root, so we may have 4 roots at the same point, and in fact, depending on the initial point, again the derivative will be 0, and higher order derivatives will be 0 as well. So this is a little bit of a tricky and problematic, but how we can determine such kind of roots and what type of algorithm shall we use? In fact, in such a case, modified Newton-Raphson method is proposed. So one approach is multiplying the f divided by f prime with m. Here m is the number of roots, that is number of multiple roots. So if you have a double root at a point, for example here m is 2, for this m is 3, and this function m is 4. So this is one way suggested. Of course, convergence is an issue, and there is another thing that can be done. So when you have a single root at that point, m is 1, but of course we can modify the Newton-Raphson by defining such a function ux, and let us define the ux, which is equal to f of x divided by f prime x. So the classical Newton-Raphson is basically xi plus 1 is equal to xi minus ux then. But it is already shown that the function ux has the same roots with the f of x. Therefore, we can use such an approximation. So if we find the roots of ux, then we find the roots of f of x, and certainly in this case u prime x is equal to f prime x multiplied by f prime x, right, minus f of x multiplied by f double prime x, second derivative of f, divided by square root of the first derivative of f. Now from here we will have the modified Newton-Raphson expression for the modified Newton-Raphson, which is seen here. Xi plus 1 is equal to xi minus f of xi, f prime xi, f prime xi square minus f of xi, f double prime xi. Now let's look at the function x cubed minus 5x squared plus 7x minus 3. So this function has a single root at point 3 and a double root at point 1. Now let's assume that our initial point is at x is equal to 0. Certainly the classical Newton-Raphson formulation can be written like this. So this is the expression for the classical Newton-Raphson. And now let's look at the convergence. So we begin from 0. Of course, relative percentage error is the true percentage error is 100% at the initial point. Then in the first iteration you reach to 0.42 and then the error is 57, the true error is 57, and it goes like this. As you see, in the sixth iteration we reach to a value of 0.977 and the error decreases to 2.2. So the convergence is a little bit slow. After 6 iterations we have 2.2% error. Okay, what if we use the modified Newton-Raphson? Then our expression for the modified Newton-Raphson is this for the function. Okay, as you see, at the initial point the true percentage error is 100%, and in the first iteration it is just 11%, and in the third iteration it is 0.31, and in the fourth iteration, or third iteration, actually we don't make any calculation for the initial guess, so initial point, and for the third iteration we have 0.002.4, so 2.4 10 to the power minus 3% error. So almost we reach to an exact root if we use the modified Newton-Raphson method for the multiple root. Okay, now until now we have seen how to solve, how to find the roots of a function, of a nonlinear function in general. So in fact, we can use these techniques, or in general Newton-Raphson method. Generally we use Newton-Raphson in order to solve nonlinear system of equations. So point is this: basically we write the equation and equate it into 0, and finding the roots, or finding the values, let's say, not saying roots, but finding the values which satisfies these equations is the solution of this set of nonlinear equations. So how can we do it? By using Newton-Raphson method. This is our objective at the moment. Now this is our formulation or expression for the classical Newton-Raphson method. Of course we can arrive this expression by using Taylor series approximation. So we will do the same thing for nonlinear problems. Now just assume that we have two functions u and v, which is needed to be which we are going to solve. U is equal to 0, and they are the function of x and y. What we do is we expand each function into Taylor series in x and y. So for multidimensional problems, the Taylor series can be written as u plus first derivative du dx multiplied by delta x, xi plus 1 minus xi, if we expand it around xi, and then yi plus minus yi multiplied by dui dy, and it is the same for value vi plus 1. Now one thing is this: we want ui plus 1 is 0. Of course vi1 is 0. We want this to be 0. Now what we do next is we expand this terms, and collect the coefficients terms related with the xi and xi1 plus 1, yi plus 1 and yi on either side of the equation, equality, let's say. And then we arrive at this expression. Now you see here I have the initial guess xi and yi. Certainly I have to evaluate the derivatives at point xi and yi, the derivative of u with respect to x and derivative of u with respect to y, and of course I have to evaluate the derivative of v with respect to x at point xi yi, and I have to evaluate the derivative of v with respect to y at point xi and vi. If I look at these expressions, the unknowns are xi plus 1 and yi plus 1. Of course, I know these values. I can easily evaluate it as soon as I know the functions u and v. I can easily do it explicitly because I know xi and yi. Now, as you see, now I have a set of linear equations. The only thing that I have to do is I need to solve this set of linear equations by means of xi plus 1 and yi plus 1. Or if you have more than 2 variables, then, for example, if you have 4 equations and 4 variables, then you will have a 4 by 4 linear system of equations, or 4 linear equations, and you need to solve this set of equations, and then you will reach to a new value of xi plus 1 and yi plus 1, and then you can check whether it satisfies the equation, and if the error is below a certain threshold, you can say that you can do this operations iteratively, and if the error, so relative approximate error, is below a certain threshold, you can say that okay, we reached to the solution. Now let's look at an example. Let's consider two functions uxy, which is equal to x squared plus xy minus 10, and that's equal to 0. So basically uxy is nonlinear in x and y. Now our second equation is vxy, and that is y plus 3xy squared minus 57, that's equal to 0. And of course this second equation is also nonlinear in y and x. Let's assume that x is equal to 1.5 and y is equal to 3.5. These are my initial guesses. So what I need to do is, for the initial guess, first I have to evaluate the derivatives. So first I calculate the du dx. Certainly du dx is equal to 2x plus y, and this is 0. So I put 1.5 in place of x and 3.5 in place of y, and as a result du dx is 6.5. Now let's calculate the dv dx. It is 3y squared. Because this term is 0, I have 3y squared from this term, and this term, derivative of this term, is also 0. So I arrive, if I substitute 3.5 in place of y, I arrive this value. Now let me calculate let me calculate the derivative of u with respect to y. So derivative of u with respect to y is equal to x. Then it makes 1.5 because x is 1.5. Now v with respect to y, so this is 1, this is 3x, and it comes 2 from here, so it makes 1 plus 6x, as you see from here, 6xy as a result dv dy. If I substitute 1.5 in place of x and 3.5 in place of y, I reach to the value of 32.5. Now I will evaluate the u and v at x is equal to 1.5 and y is equal to 3.5. Then my final values are minus 2.5 and 1.625 for v. Okay, now I have found the derivatives and the values of u and v. If I substitute everything in this expression and take out the x and y, this is what I'm going to obtain. These two equations are the expressions, or these two expressions are the expressions that I'm going to obtain. So as a result, at the end of my first iteration, for the x value, what I'm obtain is 2.03603, and for y value I get 2.843888, and the true values are 2 and y. Now I can take these values as initial guesses for the next iteration and continue. Certainly I will get closer to the exact solution if I do it again and again.